All right, to finish up our discussion of properties of light, let's look at an example calculation here. So I mentioned in the previous video about using infrared spectroscopy to look at functional groups inside of organic molecules. One that's commonly looked at is the CH stretch region. And so you know that you have CH single bonds if you see this absorption at about 3,000 wave numbers. So let's take that value, 3,000 wave numbers. So this is equal to a wave number, nu tilde, and let's convert that to what is the wavelength that corresponds to that, what's the frequency that corresponds to that, and how many joules is that per photon, right? Looking at sort of the particle properties of light. We can look at the wave properties and also the particle properties. Okay, so just to remind ourselves, nu tilde is equal to 1 over wave number, or sorry, 1 over wavelength. So if we want to find the wavelength, we can just say that the wavelength will be equal to 1 over the wave number. All right, so we can put in 1 over 3,000 centimeters to the minus 1, and we can already see the units are going to work out. We'll get something in centimeters, and we need something in length units. And that's equal to 3.33 repeating times 10 to the minus 4th centimeters. And then we usually like to convert this to other units besides centimeters. Micrometers is a common unit for infrared wavelengths. So let's take 3.33 times 10 to the minus 4th centimeters. And we like to go to micrometers. So we can say there's 10 to the 6 micrometers per meter. And there's also 100 centimeters per meter. And that's going to give us a value of 3.33 micrometers. Okay, so we found the wavelength, 3.33 microns of a 3,000 wave number CH stretch. So that's the wavelength of the light. What's the frequency? All right, well, we know that C equals lambda times nu. So we can rearrange this and say that nu equals C over lambda, or C times the wave number. Either one works. So let's do this as C times wave number. So we need the speed of light, 2.998 times 10 to the 8th meters per second. But I know already that my wave number is in inverse centimeters. So let's actually convert this to centimeters per second instead of meters per second, because we need our units to work out. So that's going to be 10 to the minus, not minus, 10 to the positive 10 centimeters per second, because there's 100 centimeters per meter. And then multiply that by our 3,000 centimeters to the minus 1. Let me give myself a little bit more space here. All right, so we can do that multiplication, and we'll get 8.99 times 10 to the 13th seconds to the minus 1, or that's the same unit as hertz. Right, so this, a lot of cycles per second, right? 10 to the 13th cycles of this light per second. And the wavelength of that light is only, 3.33 micrometers, right? So very small numbers here. And then our last question then was, how many joules is this per photon? All right, so we need E equals h nu. We just calculated the frequency. We just use Planck's constant. So we have 6.626 times 10 to the minus 34 joules times second. And then we multiply that by the frequency we just calculated, 8.99 times 10 to the 13th per second. We can see our seconds are going to cancel out, and we get something in joules. This will be joules per photon. And we get 5.96 times 10 to the minus 20th joules per photon. So we can see that's not a lot of energy, right, in the grand scheme of things compared to macroscopic things. But remember, we're talking about just one particle of light. So this is how much energy is in a single photon. So 10 to the minus 20th joules. Visible light has something like 10 to the minus 19th joules per photon. And so we usually don't talk about these in terms of joules per photon because it's such small numbers, and we usually use other units. But this just gives you an example of how we can convert between these different ways light is represented. If we're given a wavelength, we can find the frequency, we can find the wave number, we can find the energy per photon. So hopefully this is helpful.